Today we're going to be talking about magnetism and also the second half of electricity that we started last class. You've all played with magnets before, and you've probably played with magnets that have poles like these do. Magnets always have a north and a south pole, and you probably know that the opposite poles, south and north, are attracted, and like poles, south and south, or north and north, are repelled. You probably know that metals can be magnetized or not magnetized. And what that means is, within every metal are these little tiny things called domains. Domains in magnetized metals are all pointing in the same direction. That's what makes them magnetized. But the domains in a non-magnetized metal are all pointing in different directions. So if you have a magnet and all those, it would look something like this, right? And all those domains are pointing in the same direction. If you took that magnet and you broke it in half, you now really just have two magnets. And now you have two magnets where you would have, say, a north pole here and a south pole here, and you would have a north pole here and a south pole here. So magnets are made of a specific kind of metal called a ferromagnetic material, which is a material that can be made into a magnet or is attracted to magnets. And there really are only three, and they are iron, cobalt, and nickel. So iron, cobalt, and nickel can all be made into a magnet, and it's pretty cool the way it works. You may have seen someone magnetize something like maybe a needle before. You can make a compass by magnetizing a needle, and all you really need to do is take your piece of metal, and basically when you start, your piece of metal has all those domains pointing in different directions, right? And you just take a really strong magnet and you rub along that piece of metal really consistently in one direction. And when you rub in it in one direction, those domains are attracted to that magnet. Sorry, you rub the metal with a magnet. They're attracted to that magnet, and if you keep just rubbing in that same direction, all those domains will be magnetized, and you will now have a magnet. This is how you make a compass. So you've probably all heard about the Earth here, right? Which has, up here is the North Pole, and down here is the South Pole. And the Earth was labeled that way because the top of the Earth is the direction north and the bottom of the Earth is the direction south. However, the Earth is a giant magnet. And in that giant magnet, there is a North Pole and a South Pole. So let's think about a compass for a minute. If you've ever used a compass, you know the North Pole of a magnet on a compass points to the North Pole of the Earth, which doesn't make sense because it should be the other way around. The opposites should be attracting. But the reason is the Earth was not labeled as a giant magnet. It was just labeled by direction, and really kind of wrong. So the reality of it is the North Pole is the South Pole of the magnet we call the Earth, and the South Pole is the North Pole of the magnet we call the Earth. So the Earth was labeled wrong. So now we're going to switch gears just a little bit and go back to electricity. This would be kind of like part 2 of electricity. And we're going to talk today about a circuit. You probably noticed that the word circuit sounds a lot like circle. And a circuit really is a circle. Boy, that's a bad circle, sorry. In that it's a complete path for electrons to travel through. So that's all electricity is electrons traveling. And a circuit means there's a complete path. There's no broken space. So we need to have a few basic parts of a circuit. Every circuit needs to have wires. I'm trying to highlight that didn't work so well. And the wires are the places for the electricity to travel through. Those need to be made out of conductors of electricity. It needs to have a source. And the source of the electricity, sorry, didn't mean to cross that out there. The source of electricity is often a battery. And then it needs to have our thing called the load, which is sometimes called a resistor. A load is the thing we're trying to power. So it could be a light, it could be a fan, whatever it is we're trying to power is the load. So Thomas Edison is the one who discovered the invention of resistance. And he needed a way to run enough current through a wire to make it glow without it burning out. So if you have a lot of electrons together, they glow. Super cool, right? They get close to each other, kind of like people. We all love each other. When we're close, we glow with love. Well, they glow with electricity. So he knew that. But when he put too many electrons together to make them glow, they would also get super hot and they would burn out the wire. So he came up with the idea of resistance. And I'm going to show that to you on the next page. But he used all kinds of different wires and finally came up with one that works called a tungsten filament. So we'll go on to the next page. I'm going to draw you a picture of that. So take a moment to pause and draw the picture of the light bulb I drew. And I want you to think about the concept of resistance. So resistance means that's the resistor. You can see where I labeled it there. It's that little squiggly thing, right? If you think about it, all the electrons are flowing through the wire, right? And through that wire, they're flowing together. And we want a whole bunch of electrons to flow together because when electrons get close to each other, they glow. So we want them to flow together, but if we put too many close together, they get so hot that they burn out the wire. So he tried all kinds of different types of wire. He tried horsehair, he tried copper wire, he tried all types of wire, and they all just kept burning out. So he finally used a metal called tungsten, found on the periodic table, and the little resistor thing here, this is also the tungsten filament. And the way it works is the electrons, as they flow through the wire, when they get to that squiggly place, right, they slow down a little bit. So a resistor is where the electrons slow down, causing them to bunch together. And when we bunch together, they glow. They get hot, but they're still flowing in a circuit. So they get down to this bottom part right here. After they get out of that resistor, they spread back out and they cool off. And then they travel around like this. They get up here, they're nice and cool, they get in here. Here they slow down at this squiggly part and they get close together and they start to glow again and they get hot. And then they come back around to this part and they cool off. All right, so take a minute to pause the video. And when we draw electric circuits, we draw them with specific symbols. Instead of writing out the word battery or load, we draw them with symbols. So take a minute to draw the symbols I drew. The battery is drawn with these 2 horizontal and 2 vertical lines. The load is drawn as an X or sometimes as a squiggly line because it's a resistor. And actually it usually has a circle around it. The wires are just straight lines. And the switch is always drawn as open. Okay, so there are 2 different types of circuits we're going to talk about. One is called a series circuit, where there's only one path for the current to take. You need to take a moment and draw my series circuit. I drew down there for you. And you can see that you've got the 3 light bulbs here. Here's 1, here's 2, and here's 3. Those 3 light bulbs are all in a row. So if one of those light bulbs burns out, all the others will burn out too. So this is not a very useful way to have lights. They used to have Christmas lights made like this, and you probably remember from old movies where one would burn out and someone would spend hours trying to figure out which one it was because they'd all burn out. They're not made like that anymore, so it's a lot simpler. But a series circuit only has one path for the electrons to take. So the other kind of circuit you need to know about is a parallel circuit, and this is what most things are, parallel circuits. In a parallel circuit, take a moment to stop and draw it. The 3 red things are my load, my light bulbs. The yellow part is my battery. The black is my wires. And you can see that as the electrons are flowing through this circuit, if it just so happens that this one bulb here burns out, if that one burns out, there's still plenty of space here for the electricity to flow through the other bulbs. So the other 2 bulbs will stay lit. This obviously is the most useful kind of circuit. It wouldn't make a lot of sense to have a series circuit in your house. All right, last thing we need to talk about is the difference between a motor and a generator. Both involve both involve conversions, but a motor is an energy conversion that takes electrical energy and it makes it to mechanical energy. So a blender is a great example of this. A blender takes electricity, the electrons flowing through the wires, and it makes the blades spin. So it's electrical to mechanical. A car also has a motor. A car has a lot of things, but it has a motor. Once we have created the electricity, so it starts with chemical, and then that turns into electrical, and the electrical makes the wheels turn. So that's our mechanical. But the opposite of that would be a generator. A generator takes mechanical energy and converts it into electrical energy. So this is pretty important. These are opposites. So two examples of this are a house generator. You probably have seen a generator. So when the power goes out at your house, you might have a generator. And a generator takes moving magnets, and those magnets moving create the magnetic field creates an electrical field. It actually starts with chemical energy. First of all, you have to put gasoline into your generator. That makes these magnets spin, and the magnets make the electrical energy for your house. Another type of generator is a hybrid car, like my famous Toyota Prius. It takes my mechanical energy, me steering and braking, and turns that into electrical energy. That electrical energy is then converted back to mechanical energy in the form of the wheels turning.